Today, we're traveling back over 4.6 billion years to uncover the origins of Earth and its moon. The Earth formed from a mixture of dust and gas surrounding the young sun. This primordial soup gradually came together, growing larger through countless collisions between dust particles, asteroids, and other forming planets. One of the most significant events in Earth's early history was a giant impact that ejected enough rock, gas, and dust into space to eventually form the moon. Although the original rocks from Earth's earliest days have been destroyed or altered by over 4 billion years of geological activity, scientists can still piece together this ancient puzzle. By studying modern rocks, moon samples brought back by the Apollo missions, and meteorites that have fallen to Earth, scientists gain insights into when and how the Earth and moon formed and what they might have looked like in their infancy. The Earth, like all the other planets in the solar system, began its existence as a disk of dust and gas orbiting the young sun. This primordial disk gradually coalesced into solid bodies through the forces of drag and collision. Dust particles in the disk were brought together by drag forces to form clumps of rock. These clumps grew into what scientists call planetesimals, which are tens to hundreds of miles across. Through further collisions, these planetesimals combined to form Mars-sized protoplanets. The Earth reached its final size after one last major collision with another Mars-sized object. This colossal impact, known as the moon-forming impact, not only added significant material to the Earth, but also vaporized some of the rock and metal from both the proto-Earth and the impacting object. This vapor formed a disk around the Earth that eventually cooled and clumped together to become the moon. We have pieced together this incredible story thanks to rigorous studies of meteorites and rock samples, including those analyzed at institutions like the University of Chicago during the 20th and 21st centuries. Understanding how the Earth and Moon formed is crucial for reconstructing the history of the solar system. It helps answer fundamental questions such as how long planets take to form, what planets are made of, and what makes a planet suitable for life. This knowledge also guides planetary scientists in their search for other habitable or inhabited worlds within our solar system and beyond. How do we know how the Earth and Moon formed? The key lies in the study of meteorites. Meteorites bring a variety of materials from all over the solar system to Earth, allowing scientists to analyze them in detail. These materials include chondrules, tiny pieces of dust and rock that have survived since before the planets formed, and fragments of asteroids and planetesimals left behind by the planet-building process. Radioactive elements like uranium and hafnium are trapped inside the minerals that make up these objects when they form. By measuring the decay of these elements, planetary scientists can determine the age of these materials. This radiometric dating method provides a timeline for the formation of different parts of the solar system. Using these measurements, along with simulations of the physics of dust and planetesimal collisions, planetary scientists and astronomers have established that the process from dust to protoplanet takes tens of millions of years. However, the final stage of planet formation in our solar system may have taken much longer, up to 100 million years. This was not only the last major addition of material to the Earth, but also the event that formed the Moon, making it one of the most debated parts of the story. The Moon formed during a giant impact about 60 to 175 million years after the solar system was born. To determine this estimate, scientists use rocks from Earth. As large planetesimals grew, heat was released through repeated impacts and the radioactive decay of elements within their minerals, causing melting. This process allowed materials of different densities to separate, with metals like iron and nickel sinking to form a core and lighter rocks floating on top. By the time of the moon-forming impact, Earth was already separated into these rock and metal layers. However, the intense force and heat of the impact remelted the proto-Earth, remixing the separated rock and metal. After this mixing, Earth was still hot enough for the materials to separate again, forming new rock and metal layers. This remelting and reseparation is crucial for dating when the Moon formed. When rock and metal mix, they can exchange certain elements. Elements like hafnium prefer to be in rock rather than metal. Hafnium decays over about 10 million years to form tungsten. Early in the solar system's history, Earth's rocky layer contained a lot of hafnium because it hadn't yet decayed into tungsten. By the time the moon-forming impact occurred, much of this hafnium had decayed into tungsten, which prefers to mix with metal. When the impact remixed Earth's layers, the newly formed tungsten sank into the metal core, leaving the rocky outer layer with less hafnium. Today, all the hafnium has decayed because its half-life is short compared to Earth's age. However, this decay process is useful for determining the timing of events in the early solar system. The concentration of tungsten in Earth's rocks depends on when the most recent separation into rock and metal occurred. The low concentration of tungsten in Earth's rocks indicates that something remixed the Earth's layers after the initial separation. The best explanation for this remixing is the giant impact that formed the Moon, which likely occurred about 60 to 175 million years after the solar system's formation. After the Moon-forming impact, Earth was a very different planet from the world we see today. Where the present-day Earth has oceans covering much of its surface, the early Earth was covered in a magma ocean, a layer of molten rock hundreds of miles deep that was melted by the energy released during the collision. Any water present would only exist as water vapor in the atmosphere. If that wasn't enough, the early sun was also far more active than it is today, blasting the entire solar system with UV radiation energetic enough to evaporate entire atmospheres. Over time, after the magma ocean cooled enough to form a solid surface, Earth's atmosphere was replenished by volcanic eruptions, as well as water and other gases delivered by comets and meteorites crashing into the surface. This was also the first step towards our planet developing plate tectonics. Plate tectonics describes the giant plates of crust that slowly move around Earth's surface over hundreds of millions of years. It not only produces new rocks at volcanoes where the plates are moving apart, but can also recycle rocks from the Earth's surface and atmosphere back into the interior where plates are coming together. This process, known as subduction, carries rocks, water, and carbon dioxide trapped in minerals back into the Earth's interior, where they can drive future volcanic eruptions, continuing the plate tectonic cycle. Some planetary scientists believe that plate tectonics is essential for a planet to develop life. This is because the repeated production and destruction of crust by plate tectonics both releases carbon dioxide to the atmosphere and removes it, helping keep temperatures on Earth stable and comfortable for microbes, fish, and humans over billions of years. Whether a planet has plate tectonics is much more complicated than just having a solid surface, though, and might also depend on the types and amount of different asteroids, planetesimals, and protoplanets that the Earth is made of, because of the way different chemicals and minerals can change how planet interiors behave over billions of years. The early Moon, much like the early Earth, was a very different place. Most of us picture the Moon as a desolate, gray place with craters and not much else, but it was surprisingly geologically active for much of its history. Like Earth, the Moon started off with a thick layer of molten rock on its surface. However, unlike Earth, the Moon's surface did not cool to form tectonic plates. Instead, it has a thick crust made almost entirely of a light-colored mineral called feldspar. Feldspar is the main material that makes up the bright areas we see on the Moon today, known as the lunar highlands. As the magma ocean on the Moon cooled, feldspar crystallized and floated to the surface, forming a solid crust. The formation of a feldspar crust didn't mark the end of geological activity on the Moon. The heat left over from the giant impact, along with additional heat from radioactive elements, melted Boolum 11, investigating the Moon-forming impact. As we wrap up our exploration of the Moon's formation, let's delve into the innovative methods scientists use to study this monumental event. Some experiments can be too large for the lab, so computer simulations play a crucial role in investigating the Moon-forming impact. These simulations allow scientists to virtually smash together the proto-Earth and various types of planetesimals at different speeds and angles. By doing so, they can determine which combinations of properties are capable of forming a moon with the size and orbit we observe today. In the future, new samples from the Moon could provide planetary scientists with a wider range of different lunar rock types to study. This is vital because new samples might reveal different aspects of the Moon's history that aren't present in the lunar rocks brought back by the Apollo missions. As measurement techniques improve, scientists will also be able to detect new chemical signatures in lunar rocks and enhance existing measurements. The more measurements scientists gather, the more ways they can test different theories about how our moon formed, its relationship to Earth, and even how moons might be born around other planets far beyond our solar system. Thank you for joining us on this incredible journey through the history of Earth and its moon. If you enjoyed this video, please like, share, and subscribe to our channel. Hit the notification bell so you never miss an update, and leave a comment below with your thoughts or questions. Together, let's reach for the stars.